welcome back to this course on combustion in air breathing aero engines. So, in the last class we were discussing about the governing equations. So, as we discussed that we have discussed of course chemical kinetics in a very detailed manner, and we have discussed how the reaction rate changes depends upon various factors like temperature, species concentration, etc. But only that information is not enough, because in a flowing system, in a practical engine, you have convection, you have diffusion, and also you have other things. You can have other things like radiation, etc., which basically it means that the combustion parameters like species, temperature, these are also affected by the flow, the nature of the flow inside the engine, right. So, to couple the flow and the properties like species, concentration, temperature, we need governing equations, and you have seen that how using the Reynolds transport theorem we can go from the description of a system to that of a control volume, and we have derived the governing equations for we have described we have obtained the governing equations in terms of conservation of mass, which is the continuity equations, and we have species equations, momentum and energy. And so, these are the equations that we have as you see we have obtained. We have obtained the continuity, which is dou rho d plus divergence of rho v equal to 0, species equation, momentum and energy equation of course. But as you see that these equations A are quite complex, even though they do not look so complex. The thing is that many of these parameters, many of these quantities like the diffusion velocity, like this quantity, the pressure tensor, the heat flux, okay, body force, etc., many of these are unknown, and we need to provide auxiliary equations and constitutive relations to close and to solve the equations, okay. So, for that these are the things, as we have seen, that we need to supply equations for diffusion velocity, pressure tensor, heat flux vector and reaction rate, and this is the reaction rate of course, and which we need to basically close these equations. And here is this diffusion velocity. Now, note there is a small connection with respect to previous class. This diffusion velocity, which is actually implicit in terms of the species concentration gradient of xi, but here there is a summation from summation over j. So, that this gradient of xi for there is a gradient of the species concentration of the molar concentration of the ith species, gradient of xi is essentially summation over j to 1, that is for all the species other than I, is given by xi xj divided by dij, which is the binary diffusion coefficient, and which we obtained in the, if you remember, in the previous transport phenomena class, times vj vi plus this things arising out of gradient of p, gradient of t, etc. All right. And of course, this pressure tensor that we discussed, which is the standard description. So, this is the pressure, this is the bulk viscosity, and this is the strain rate tensor, which multiplied with the dynamic viscosity gives you the shear stress basically, okay. And also the heat flux vector we have discussed, which also comes out mainly from conduction, gradient of temperature, this is the thermal conductivity. Then also the heat flux vector can be affected through the different heat content of different species, and also due to temperature, also due to molecular diffusion velocity, and of course due to radiation. And then we have of course discussed reaction rate in great details, and this is the reaction rate formula that you see. And of course, one important point to note is that this is units of gram per cubic centimeter, whereas in the kinetics class we obtained reaction rate in terms of units of mole per cubic centimeter, and this is the difference that arises, that we need to take into account the molecular weight of the species I. Okay, so once again note here there is a correction, the summation of j, summation goes from j equal to 1 to n instead of I equal to 1 to n. So, when this thing is that of course this means that this gradient of the concentration which can arise due to this difference of the species diffusion velocities Vj minus Vi, and due to pressure gradient and due to body force difference and due to temperature gradient. Now, these are typically negligible in a we will neglect this unless this specific situation arises, but mostly we will neglect this in combustion for discussion. This is also typically negligible, that this is a Sorate effect, arising out of temperature gradient, and we will discuss this in great detail. So, we will mainly consider that our species diffusion will mainly be concentrated into this region, and we will neglect all these things unless otherwise mentioned. Alright. So, these are the different things out of temperature gradient, pressure gradient, body force, and concentration gradient, and temperature gradient, etc. Now, we will go we have already discussed this. So, we will not go into these different things, how the heat flux vector changes. This is just a recapitulate, and of course, we need the auxiliary equations like P, we need the equation of state, we need the energy enthalpy relations, and of course, remember that the total energy that we discussed is essentially the sum of the enthalpy of formation plus is the sum between the enthalpy of formation at temperature T0 plus the sensible enthalpy at temperature T with respect to the reference temperature T0, and of course, this sensible enthalpy can be written as integral T0 to T times Cpi, where Cpi is the specific heat of the ith species times dt. Okay, and then of course, we frequently need to convert between mole and mass fractions, because the species equation is given in terms of mass fractions, whereas your reaction rates are written in terms of mole fractions. So, here is how you convert it. Xi is equal to yi divided by wi divided by summation j is equal to 1 to n yj by wj, and this is the how to convert from mole fraction to mass fraction. Alright. So, these are the things. And then we simplified that if we assume that this is we only consider this the only consider that the gradient can arise due to that only if we consider the concentration gradient effect on diffusion. So, this is what we are basically have left with. Here you see that xi, the xi was here. So, the xi has basically spins with a summation over j. So, the xi has come over here. So, actual equation was gradient of xi is equal to summation j is equal to 1 to n xi xj divided by dij times vj vector minus vi vector. So, if since this we have neglected other terms, now the xi can escape this thing and it can come over here. So, when it comes in the downstairs in the denominator, it becomes log of xi, and now you can apply several simplification, that if you can apply equal diffusivities, then this becomes simple, and then you can write it explicitly vi is equal to minus d ln minus d gradient of ln logarithmic natural logarithm of yi, and this is the fixed law of mass diffusion. But a better assumption is that we instead of equal diffusivity, we consider that dij is equal to din, where n is the abundant species, and this is a good assumption, because you see that of course, in air we are considering air breathing combustion in air breathing in situations when the oxidizer is air instead of pure oxygen, and when there is air, the abundant species is of course nitrogen, which is about 71% by volume in air, and of course, the fuel mass fraction is very small, and oxygen mass fraction is mole fraction is also small, 21% by volume, and so mainly it is nitrogen, and so we can think that all the species, whether it is fuel, whether it is oxygen, is basically diffusing in a sea of nitrogen essentially. So, we can consider this dij is essentially din, where n is the abundant species, which is for example nitrogen, and then we can write that that vi is equal to minus din, where n is is basically the din is essentially the diffusivity of ith species with respect to the nth species, which is the abundant species, and then this becomes gradient of ln yi. Alright, and then we, depending on the situation, we assume that rho d is equal to constant or rho square d is equal to constant, and this will become evident later. And we have also gone over isobaric assumption, which by which we showed that the for subsonic flows essentially we can consider this equation itself, because the equation between a reacting and a non-reacting flow, the momentum equation, this is essentially the momentum equation, is not different, because momentum is essentially conserved in chemical reactions, and the only difference is that when you have reacting flows, your density changes, right. So, that is how reacting flows are differentiated with respect to non-reacting flows, at least in terms of the momentum equation. But what I want to say here is that order of 1 to effect order 1 acceleration, you only need an order of Mach number square of pressure gradient, and as a result your pressure is essentially the spatially is essentially constant within the within your combustor. It of course drops for a little bit for in subsonic flows, and it increases in supersonic flows, for example. So, in a gas turbine engine you have a small pressure drop downstream in the combustion region, downstream of the combustion region, that is in the product gases, whereas in scramjet combustion you will see that you will have essentially a little bit of pressure rise in the combustion gases. All right, in the product gases essentially. So then we have considered that this is the background pressure, P0 is equal to rho RT, and P1 xt is equal to the dynamic pressure, and then we need to basically what we want to do here is that we want to derive a simplified set of equations for diffusion controlled systems, and we will do that here. Basically let me just do the derivations. This is important, and so that these are the assumptions that we will specialize to subsonic flows only, and only 4 minimum key processes will be included, right. So, we will include unsteadiness, we will include diffusion, that is the we will include the mass, and we will include species diffusion, and we will include thermal diffusion, that is conduction. We will include convection, and of course we will include reaction, because otherwise if we do not include diffusion and reaction, then it does not really describe a real combustion situation. As you will see that in certain cases we will be able to neglect convection, not of course inside an engine, but when we were discussing about a simplified system, for example in a one dimensional non-premix flame or a one dimensional premix flame, we will be able to neglect convection, and essentially this then the systems will essentially be a competition between your reaction and your diffusion, and that will come later. But anyways, so but we will not go there right now. We will just have these 4 processes included: unsteadiness, diffusion, convection, and reaction. And you will see that the derivation only involves energy and the species equation, which are explicitly affected by reaction. So basically the thing is that, as we have seen in last class, and today also, that in the low Mach number limit your pressure really does not change, and as a result your pressure gradient is very small. So your momentum which is rho u times u, even though that changes by a small amount, it does not really will consider a very simplified point of view for momentum. So that whatever the gas accelerates, that can be computed through the continuity equation, and there is no really change of momentum as the pressure gradient is small. So there is actually, if you see that that can be essentially explained from this isobaric assumption, that once again if you go back, this within this non-dimensionalized form, if you have to create an acceleration of order of 1, this will be this pressure gradient will be order of Mach number square. That was the thing, and so of course the flow accelerates in a reacting flow, as you see, but then this will consider that this acceleration can be computed. This acceleration can be computed essentially through the continuity equation for the systems that we will consider, and the momentum equation will not be really discussed explicitly in our derivation. So this derivation we will only include the species equation and the enthalpy equation. Okay, and enthalpy equation, we will see that it does not come explicitly. We will actually start with the internal energy equation that we have derived, and then from the internal energy equation we will combine this with the species equation to arrive at the enthalpy equation. So that is what we are going to do first. Okay, so the equation that we have, if you see, the equation that we have derived previously was this. This is the rho times d, this is the material derivative dE dt is equal to partial dou derivatives of with respect to time over rho e plus divergence of rho v vector, this is a small v vector, that is a bulk fluid velocity times the internal energy is equal to minus of grad q minus p v. This means that the tensor has to be contracted twice, plus this is the diffusion velocity. Now, what are the terms we can get rid of? This, of course, we assume that there is no body force, so this goes to 0. Okay. This can be shown to become simply P times divergence of V, whereas now P is a scalar essentially. All right. So, then this becomes okay. Whereas q vector, that is the heat flux vector, is equal to minus lambda grad T. This is the conduction term, right? This is the conduction term, plus rho times summation I is equal to 1 to n h I y I v I. This is the species diffusion velocity. Okay. So, this is, as you see, that we have left out a lot of things, but this is the most simplified form of heat flux vector that we can write at this stage. All right. And of course, as you have seen that the V I is given by, if it is a simplified system, if we use Fick's law of mass diffusion, it is given by V I vector is equal to minus d I with respect to n times gradient of x I. All right. So, that is how V I can be given. Or if you want to use the full diffusion equation, you can write the gradient of x I is equal to summation j is equal to 1 to n x I x j divided by d I j times v j vector minus v I vector also. All right. Now, what you can do is that you can write E, that is the internal energy, is equal to H, that is a specific enthalpy, by minus P by rho. That is the definition of enthalpy. H is equal to U that is E plus P by rho. Of course, this is specific quantity, this is specific quantity, and then if you substitute this into here and write that H is equal to summation a bulk specific enthalpy is equal to summation y I h I is equal to y is equal to 1 to n, then this yields that is, this is the transient term dou dou t of rho times summation y I h I plus this is the gradient of bracket density times summation y I h I plus v vector plus v I vector minus lambda grad t. I will explain this term in a second, is equal to dp dt. Okay. So, this is the transient term, this is the basically the convection term, and this is the species diffusion term, and this is the heat flux crossing the boundaries. This is also the heat flux crossing the boundaries, and that is carried over by the species diffusion velocity. This is heat flux carried crossing the boundaries due to temperature gradient, and that is equal to dp dt. All right. So, this is what we have derived, but you see here interestingly there is no reaction rate happening. So, how does the, where does the reaction rate come in? Now, if you want you can spare us, you can just pause here and just think where does the reaction rate can actually come from. The clue is that you remember that this is total enthalpy. So, total enthalpy of course contains as we have seen that the total enthalpy H I is nothing but H I 0, that is enthalpy of formation plus H I sensible. Right. So, these two things. So, now you can think that where does the reaction rate can come from. And of course, when you have invoked this is not enough, now we need to also include species conservation equation in this one somehow. So, the species conservation equation is given by this is of course the energy equation, and this is the transient term, and this is the essentially it will contain the convection term of the species yi v vector, species convected to the bulk fluid velocity, plus the species crossing the control surface or the element here due to the species diffusion velocity vi, capital Vi, and that is equal to the reaction rate term. Once again, this is W and not omega, and this is goes from I is both equations go from I is equal to 1 to n. Right. Now, what you can do is that now you can multiply this equation on both sides by hi0 and then sum over from so this is multiply this equation with hi0 and then sum over I is equal to 1 to n. All right. If you do that, what you will get is that, so what we have done is that we have derived the enthalpy equation, and we have also in a simplified form from we have derived the enthalpy, the total enthalpy equation from the internal energy equation, and we have simplified it in terms of the, we have neglected some of the terms. We have got a simplified definition for the heat flux vector that is crossing the element surfaces, essentially element boundaries, and then we have obtained the species equation, and that is also in a simplified form, and then we have multiplied with the species equation enthalpy of formation, and then we have summed over from I is equal to 1 to n, and this new species equation that you get, if you subtract from the previous enthalpy equation, the total enthalpy equation, you will get what will you get? You will get the equation for the sensible enthalpy, right. So, you have just to give you an example, you have got an equation for the governing equation for Hi total, and then you have got an equation for Hi0, and this is obtained by the which is obtained by Hi multiplying Hi0 times Yi, and then the governing equations for that, okay, and then this was the governing equations for His, and then if you subtract between these two things, what you are left with is essentially the equation for His, because Hi is S is nothing but Hi minus Hi0. So, what you get is essentially, you should do the derivations yourself. I will just write down the final answer here. That is the equation that you get is nothing but this one, density. This is a very important equation, because this is the equation that we use for all our combustion calculations, and this is also the equation either this form or in a temperature form that appears. So, this is the convection term plus this is the rho times summation I is equal to 1 to n. This is once again the enthalpy, the sensible enthalpy that is crossing the system boundaries due to different species, due to different actually we will see that this is due to different specific heats, minus lambda T is equal to dP dt minus, now you will see the magic, I is equal to 1 to n. Okay. This is nothing but the heat release rate. Why? This is your reaction rate, is the species consumption rate, and this is the enthalpy of formation. So, when you sum over I is equal to 1 to n, you essentially get the heat release rate, that we will see, and this is what is actually changing actually increasing the sensible enthalpy before and after the reaction with respect to the state previous to the reaction. Okay. So, this is our very important governing equations, that is a species enthalpy equation, and of course, here Hs is nothing but summation is equal to 1 to n yi h si. Okay. So, this is the species enthalpy equation that we have derived. So, this is how you go from essentially you go from essentially you go from the internal energy equation to a sensible enthalpy equation, and I would strongly encourage all of you to just derive this equation yourself. It is not very difficult at all.